Today we'll talk about engineering measurement and estimation. As engineers, we know measurement is an important factor of our daily life. We always have some sensory measuring something for us. Sometimes we have manual tools that we use to be able to do certain measurements either within the design phase or within the testing phase to do our job efficiently. Now, the objectives of this chapter would be we will perform numerical calculations with measured quantities. We will determine as well the number of significant digits in a measurement, and we learn a little bit more about what is significant digits means, how we can identify what kind of significant digit we should use as we are writing down or typing in our measurements. We will talk a little bit as well about defining the accuracy and precision in our measurement, try to differentiate between accuracy and precision, and hopefully we'll move on to solve problems that involve estimation of data, assumptions, and measurements. Now, as an introduction for this chapter, and we need to know that knowledge is valuable only if we can express that in numbers. Again, numbers is the engineering language. An engineer who don't know how to handle numbers, between quotations, an engineer who don't know math, all types of math, either simple or complicated, that is necessary for his job, that means he's a weak engineer. You need to be able to spend the time needed to learn more about the mathematical functions and processes and operations needed to do your job. Each job needs a different set of mathematics. This is why while you're in your engineering degree, you learn a lot of mathematics. Some of them never use, some of them use it a lot, but you don't know where you end up in which field. So it's important to teach you as much as we can, and we will be able to analyze and design as we're moving forward in this chapter. We did that a little bit before, but we need to know as well, analysis and design needs measurement. You can't design something without measurement, either through visualizing that kind of design, or maybe you need to create a new design. So you gotta measure the old design and move on with that. And you need to do all the calculations needed to be able to deliver an accurate design. Measurements in more details, we have two concepts. The first concept is accuracy, and the second concept is precision. Regardless of the definition, so if you're targeting this kind of circle within a circle, and all your targets are being dead center, what does that mean? It means accurate and precise. We know that in our daily language, we say accurate, like that guy is dead accurate. Every time he shoots in his air gun, he just get it in the center. And now, if we shoot all the targets, or all the bullets, whatever you call it, or the bows, or the arrows are hitting this side, all of them in the same location. So so in this case, it's precise but not accurate. As long as you are hitting the same target, you are precise. In our minds, the daily language we use, we say accurate. Somebody hitting things always in the same spot, he's accurate. But the engineering term, I would say, is precise. Everything is in the same spot, but it's not accurate because he didn't hit the dead center target in this case. Now, if you had them scattered but somehow around the center of the target, like he was targeting in the center, he had one in the center, the rest are in just the next circle out of the center. So in this case, what do we call it? We call it accurate but not precise. So he's accurate, he hit near to the target we need, but he's not precise. Not all the arrows are hitting the dead center. If we go here, we have all his arrows are scattered around the circle, some of them near to the center, some of them very far, maybe some of them off. In this way, we say not accurate and not precise. Accuracy can be defined as the measure of the nearest value to the true value. In this way, you are accurate. If you are heading near the center, you are accurate. Precision is the repeatability of your measurement. Every time you do a certain action, you are getting near to the previous action or to the previous result. This way you are precise. Of course, don't think about it only about bullets or about arrows. It could be any other form of engineering application. So now if I say, well, I mean, I'm too much fan of automotive field and vehicles and stuff, so I'll draw an ugly vehicle here. Go from 0 to 60 miles per hour and measure for me how long it took you, how many seconds to reach from 0 to 60. You did it the first time. 0 to 60 took you, let's say you have a Ferrari over here. It took you maybe 3.6 seconds for the first time to reach from 0 to 60. The second attempt, you got 3.4 seconds. The third attempt, you got 3.3 seconds. The fourth attempt, you got 3.7 seconds. In this case, I know it could be a kind of jelly style example, but I just want to emphasize that it could be anything else. That's only to provide you a concept. So here, what you would call these data. You plug them in Excel, you said, well, here's the speed and here's the time, right? Then you start to say, okay, always the speed is 60. Then you put them in your Excel, you want to draw a graph, right? Speed versus time. 3.6, 3.4, 3.3, then you got 3.7. So you can see all the data combined to the right moment. What if the manufacturer is telling you from 0 to 60, this Ferrari vehicle should be able to do it in 3 seconds? So this would be our accuracy reference, right? In this kind of example. As close you are to the 3 seconds, and depend how close you are. This is why we said as an engineer you need to be specific, because how close is close? Is 3.1 close? Is 3.6 close? So I would say any of these, we would say not close enough to the accuracy. So here our accuracy is bad because we're not close to 3, 3.6, 3.4, 3.3, 3.7, but all our speeds are kind of in the same area over here, while this is your accuracy. This is 3 seconds, but all your speeds all your times are here. You got here number 1, 2, 3, and 4. The first one to the left with icon number 1. What would you call this? We're talking precise or accurate, precise and accurate, precise and not accurate, any combination. What do you think? All in the dead center and all combined together at the same point. What do we call this? So high accuracy, high precision, or precise and accurate, we know you mean high accuracy. How about the second one? What do you think? Low accuracy, high precision. And the third one, it's debatable, but since we saw the first and second are too close to each other, that's called precise. So I would say this way they are scattered, so they are low precision. Okay, the fourth one, low accuracy and low precision. That's right. Now, significant digits. How many of you heard of significant digits? Perfect. That would make our life easy. Now, in engineering, I would say generalized word, but just for the sake of walking you through significant digits. There's 2 types of engineering numbers. We have the integers, what we would call them as exact, and we have the real numbers. Real numbers could be exact or could be approximate. So remember, in other courses, MATLAB, for example, we call encoding, they use the word integer. Just don't mix both. It could be sometimes true for both in real life mathematics and in MATLAB. Sometimes it's confusing, so don't take MATLAB as your reference, just in case. Integers, you have 1, 2, 3, 4. If you tell me 3, I know it's 3 apples. There's nothing else. There's no doubt in it. It's exact number. I need you to give me 3 apples. I need from you $2. That's it, $2. You can't give me $2.01 if I told you $2. Now, if we say how many eggs are in a dozen, assuming the dozen have 12 allocations, we would say the dozen of egg have 12 eggs exactly. In this case, it's exact number. Now, I would say the ratio of the circumference of a circle to its diameter. Everybody knows circumference? That's the outside area of the circle. Okay, now the ratio means circumference divided by diameter. So I would say, well, that's approximately, which is the pi in this case, approximately 3.14 you could go more detailed. You could say 3.142. You could say 3.14159. All depends on the precision that you require in your numerical calculation. You know the concept of rounding in mathematics. So there's, if the number is too long, the pi could go like, I believe, 50 numbers after the point. So 3.14257, so on. So you round up to the accuracy that you want. Maybe 3.14 is enough for me. Then I would say it's approximate number because the real number is going way longer. Could be going to infinity. Now, any physical measurement that's not a countable number, that means we approximate it. That's in simple terms. I give you 2 apples. How many apples you got? I got 2. While there's some values, back in that example, the pi real number is 3.142789 to infinity, right? So you can give me any approximation to that number and you still approximate. I couldn't say it's wrong, but it's not the complete number. That kind of thing. So when you have a physical measurement, I tell you, measure the table width for me, or thickness. Then you say the thickness is 10 millimeters, or say 5 centimeters. Then I can't tell you, no, it's not 5, it's 5.002. I can't, as long as it's measuring 5, If it's something else, then it's measurable, or I would say approximate. We will talk in more details as moving forward. Now we have here an example of a ruler. Then we need the length in blue. You need to measure for me. This is the 0 for the ruler, as you know. Going to the right, and that's the length in blue. Now, how would you tell me what's the length over here? And that will touch on the note that we mentioned. If it's not exact, then it's approximate. Now I tell you, measure from here all the way to here. I gave you a notch. You gotta approximate. So it's not coming on a grade exactly. It's coming somewhere in between, but maybe too much towards the right or to the left between these two. That's where approximation starts to show up, I know we are in the digital age and there's laser measurements can give you, dead accurate measurements, but in the old style, and you're still in the industry, you'll be able to go into a situation where you got to measure, but not very sure what's going on, either in inches or in centimeters or in millimeters. In this case, we're talking inches. So we have 1 inch, 2 inches, 3 inches. Now I want to measure here. Help me. If it's not big enough, we can zoom it for you. So what do you think? Who's going to help me? Now the first thing we do, we say, well, we all agree it's between 2 and 3 inches, right? Okay, now we got to squeeze it down. It's between 2.6 and 2.7. Then now, if I told you, well, just give me approximation between 2 and 3, where it should be, you would say 2.5, then that's kind of engineering way we do it. We say plus or minus what in this case? So if I say, give me a number, I don't want to be very accurate all the way here. Just give me an estimation. 2.5 plus or minus. Because it could be 2.5, could be 2.5, could be 2.6, 2.7. So you're talking about 0.5 of an inch in difference, right? So it could be 2.5, could be 2.6, right? Yes. So that's why it's like plus and minus 0.5. That's the accuracy for you. Now, if you want to look closer, you got 2.6 and 2.7. So you could say 2.65 plus or minus what?
0.5.
Plus or minus 0.5. So now we are more accurate than the first number, but all are approximated. I can't say wrong for the first one. I can't say wrong for the next one. But this representation is more accurate than this representation. But you are an engineer, you are in the field, you got to call a number. You can't give me this to the project manager or the designer to do a certain modification. So you got to give him something. So do your best judgment. So we are agreeing this is better than this. So the measurement here, 2.65 plus or minus 0.5. So it could be 2.66, could 2.67, 2.68. What should we choose? We see, is it closer to the 2.65 or more to the right? And based on that, we measure. I see in this case, it's So the author is saying here it's going, if this is 0.5, like 2.65 is here, he's saying it's a little bit backward. Now here again, we have a temperature gauge, I don't know why in blue, and you got this arrow here. Start with the arrow. What do you think is the best? Following the same approach, what would this arrow represent? What is the approximated number that this arrow represents? So we said we take it from the farther distance and squeeze it down to the high accuracy. So following the first approach, I don't know, I would say this is in centimeters. 1 centimeters, 2 centimeters. Now, there's 1, so this would be 1.5. This is 1.5. So from 1 to 2, so for 1 to 2, if you want inches, we can do it inches, that's fine. Now, 1.5, what should I say, plus or minus? Maybe in this case, it's more than 1 grade, right? So 1.5 here, you can't say plus or minus 0.5. 1.27. So I could say here 1.5 plus or minus 0.2. That's one way. If you want to get more accurate, so it would be either 1.26, 1.27, or 1.24, right? Now, that's where we squeeze it here. Now, if you want to go in more details, then I would say 1.26 plus or minus. It's approximate. So you're trying to roughly know what's going on. So I would say 52.5 plus or minus 5. So 52.5 plus or minus 0.5. If I want to be more accurate, what should I do? I would say 52.5 what? So if you want to represent it in more detailed, significant figures, what we're going to do? 52.9, what do you think? 5 plus or minus 0.05. This number is more accurate than this number. Both of them are estimates or approximates, but this guy is higher accuracy than this guy. But yeah, if you are solving a problem, you should get all the grades and they'll be obvious and what kind of scale you're using and all that details. Now, the conventions for the number presentation. As engineers, we present the number in a different way. Probably in your scientific calculator, you know there's the standard way, there's the scientific way. We talked in other courses as well on how to represent number in different ways. Now, there's some kind of side rules that's good to know. For the numbers less than 1, the 0 is written in front of the decimal point so that it will omit any possible errors. What does that mean? Instead of putting 0.345, you put 0.345. And that's something personally I fall into. Many times in my real life, I just ignore that 0. I just put 0.345, but it's easy somebody else to write it, to read it 345, because your comma or your dot is could be not showing and not readable. Now, a space that's not used almost anywhere. Space is used to divide numbers of 3 orders of magnitude and more. So we have 4,567. You would say 4 space 567.8. But we know that it's more in the US used are 4. Then you have comma 567.8. Right? In banks we see them using the comma more than the space. But the right way is to have a space, not a comma. And if you have 0.678, not only for big numbers, even small numbers, 0.678, then you have a space 91 instead of having the whole thing as 0.678, 91. And for the very large numbers or very small numbers, we use the scientific notations so that we can reduce the size of that number. Probably you saw that in many courses. So you would say 478.2 multiplied by 10 to the power of 12. And instead of having 478, then 209 zeros in front of it. You just represent it by multiplication to the 10 to the power of 12. That means there's How much? There's 12 zeros in front of that number. We use prefix for the gigantic numbers. We have even bigger numbers than that, so that we can make it easy to write and handle. That is representing the mega, tera, giga, and even for the small numbers, milli, micro, and so on. I believe you guys are familiar with that. I'm not going to stop to it for so long. You have a table here for all the units used for what I call them as gigantic numbers. Like those numbers, you just keep writing zeros all along as you're doing a simple calculation, which doesn't make sense. So the tera is 10 to the power 12, abbreviated as T. The giga, you know that from the computer science, from your knowledge with computers and phones, you know that. Giga 10 to the power 9, mega to the power 6, kilo, hecto, deca, deci, and so on. Then you have something here for the small numbers, milli, you know that, micro, nano is 10 to the power minus 9, pico, 10 to the power minus 12, femto, 10 to the power minus 15, and the atto, 10 to the power minus 18. Did you guys heard of femto before?
We just went through all that in chemistry.
Chemistry? Perfect. You did?
Femto?
Yeah, the femto came in chemistry. I'm happy to elaborate a little bit on that. So you have in chemistry, let's say, so you have two atoms of hydrogen. They will be free in space. This is H1 and this is H1. Then they used to have microscopes to look at them for the chemistry scientists. Then they know, they see this moment. Then they see it already H2. They don't know what happened in between. It just happens so fast that you can't see it with the modern microscopes. Then a guy from Egypt origins called Ahmad Zuwail, he was working, I believe, in Caltech, and he came in, he used laser kind of microscopic technologies and assigned like the old technology with the new technology, and he been able to video the moment while the H1 and H2 are combining together. So it was happening too fast, but you would say he cracked the time because the microscope couldn't catch this moment, so he made the light reflection faster. It's like he slowed down the time. So you would be able, by that moment, that was the first time human being saw the femtoseconds in real time. So he'll be able to see how the two atoms coming together, and he got Nobel Prize on that, which was amazing. So that's something just on the side. Femto is too much little, but that was amazing, the efforts of those teams who could do it. Now, what you do in rounding, assuming you never heard of it, you increase the last digit retained by 1 if the first figure dropped is greater or equal to 5. So you have 4.569. Now, I want to tell you to round to what, or you're going to decide you round to what. So you have here 4.5. I tell you round to the 10th. So this is the tens before the point. After the point, you have the 10th, the hundreds, and the thousands. I tell you round this number to the 10th. 4.5 would be, I'll look to the right of that number. Is it greater or equal to 5? Yes, then I'll add 1 to the number 5. So you get the number 4.6 as a rounding for the number 4.569. Now rounding 23.650 to the 10th would be 23.7. Rounding 0.0143 would say to the, I believe to the thousands here would be 0.014. Rounding 827.48 to the 10th would be 827.5. I believe you guys know that. Now for multiplication and division, how you're going to handle the significant digits in those cases. Now when you have a product or multiplication of the operation, that should contain the same number of significant digits as contained in the number with the fewer significant digits. What does that mean? If you multiply 2.43, it has 2 significant digits in this case, multiplied by 17.675, it got more significant digits. How should your number look like? In this case, he said you go with the number with the fewest significant digits. So you should contain 3 significant figures. So either you say 3.0 or you say 4.30 multiplied by 10 to the power of 1. You guys are good with that? Okay. Now for the other number, you would say 2.479 multiplied by 60. And remember, if I give you only 60, that's 60.000 as much as you want. So you go with the least one, which is 2.479. Then you go, your result would be 148.7 or 1.487 multiplied by 10 to the power of 2. Now for addition and subtractions, the answer should show significant digits only as far to the right as seen in the latest precise number in the calculation. What does that mean? If you have 1,725.463, you add it to 189.2 plus 16.73, you see here 189.2 is the least precise. Remember we talked the more digits you got, the more precise the number is. So that's your least precise. Now your result would be with 3 digits to the right of the point. So it would be 1931.393 that you would write as 1931.4. Guys are good? Okay. Now if you have combined operation, it means you got more than one operation, could be division, could be subtraction, addition, and so on. If the product or the quotients are to be added or subtracted, perform the multiplication or division first. That's how you do it. And you follow all the rules for division and multiplication to get the significant figures. Then you establish the right number of significant figures. Then you perform your addition and subtraction to reduce complexity in this case. And eventually you round to the proper significant figures. Now we will talk a little bit about errors. All measurements of physical quantities have certain amount of uncertainty. Uncertainty means errors. We try as engineers to make errors as small as possible, and we try as well to account for errors in our measurements. You know, in many sensors you're going to handle in your life or in the industry, many sensors need calibration. When you open the sensor sheet or the box, you'll find calibration sheet when it was calibrated. What is the 0 for that sensor? You know, some sensors start with the number 2 and the rest is the real values. Some sensors start with 0 as regular as any other accurate sensor. All depend on accuracy and the calibration method used. So you got to keep that in mind. If you are measuring the temperature so that your AC will work in a certain way, you better know what's the offset for your thermometer and account for that in making the compressor pumping, you know, more power and making maybe the space cooler and all that stuff. So you can see here we have on the right thermometer. Now we have 2 types of errors that applies in coding and applies in physical life. Systematic errors and we have random errors. Systematic errors, you would say it's accurate, it's precise errors, as we just learned in the first of the lecture. All the errors are falling into the same spot. So you can see they are not accurate, they are off, but all of them off at the same spot or range. So they are precise, but they're not accurate. That's systematic error. While random error, just, you know, the target is going all over and your data is going all over. None of them is being accurate or precise. So you can define systematic error as shifting a measurement consistently in the same direction from the true value. Such error would be the calibration for your sensor, could be forgetting to account for external errors. Random errors would be errors fluctuating from one measurement to another for the same instrument without actual or real cause, and there is no patterns into it. It's just random. Now there's another thing to keep in mind other than approximation of numbers. There's the estimation. Some people define estimation as the fine art of guessing. It's another face of the coin for probability. Engineers always do their best to get the high level of precision in their work, but engineers can never be precise regardless how genius they are. We need always to have acceptable precision in many situations. You need to know, as working on a project, how precise they need the data and the output. Engineers are expected to estimate the result with an accepted accuracy while they keep the time and cost in their mind. Let's take the final example for this lecture today. We have an aerospace engineer asked to sit in a meeting of executives for an airline considering to purchase the Boeing 787 Dreamliner. Now, that engineer is asked if she could give the group a quick estimate of the average cruise fuel consumption on a per mile basis. Like how much fuel is consumed per mile. You know, the airplane will have taxiing on the airport until it's in the right location to take off. Then you will do the takeoff and you'll do the landing. But in between, there's a cruise. That's where you hear the beep and they tell you can eat, you can drink, you can do whatever you want and take off your seat. That's the cruising time. Now, they need to know how much miles per gallon, or I don't know how they estimate that, per miles basis, how much fuel is being consumed. The executives can use the result so that they compare the 787 with the competitive aircraft. Maybe they can go with some other vehicle or other aircraft which consumes less aircraft fuel, I would say, as they're trying to make their final decision. Now, you know, it's kind of a generalized way to approach the solution. We're just trying to walk you through the process here. How did he do the estimation to find his final answer? Just a way of thinking, you know, we're not gonna ask you that kind of stuff. The engineer specs published by Boeing about 787 aircraft, that's what he looked for. Remember we said collecting data in the past? So he looked at the specs of that specific aircraft and he looked at the numbers or the ranges estimated for the base model of that vehicle. It was 7,650 to 8,200 nautical miles, NMI. What's the difference between nautical mile and regular mile? You know, in regular mile, you would approximate as a linear line from point A to point B, that's your mile. While the nautical, you know, there's a curvature into Earth. As airplane is flying, it flies into kind of curvature, depending on the path being written. So the nautical mile equals 1.15 of a regular mile on Earth. Just, I thought, something to keep in mind. Now he estimated that. He knows what's the numbers for the range of that exact aircraft. Now he found the cruise Mach number, M, to equal 0.85. What's the Mach number? It's the speed of the aircraft divided by the speed of sound. In air jets or jet airplanes, military purposes, you would say, oh, this airplane is Mach 3 speed or Mach 5. It means 5 times the speed of light, 5 times the speed of sound, 3 times the speed of sound, and so on. Now, the fuel capacity for that aircraft is 33,000 gallons, which would be in pounds 220,000. 10% of the fuel is used during taxi, takeoff, climbing to altitude. 10% of fuel is reserved for emergencies. Now, he calculated the cruise fuel consumption per mile to be, he divided 26,400 divided by 9,436, then he got 2.8 gallons per mile, which would be in pounds per mile as 18.7 pounds per mile. Now, as he did that approximation, the executives can now estimate the fuel cost per mile depending on the current fuel price. So that's kind of the mentality you need to have as looking into estimation. He didn't know, maybe that day the temperature is lower than normal on that altitude. Maybe the emergency, the tower in the airport told them to go on a lower altitude, which would increase the consumption of fuel. But at least you get an estimate of how much would it consume while cruising and get the fast decision for the executives.